We want to find a formula for Taylor polynomials of order n. We've already talked about the polynomial of third order, P3, and we've gotten this formula for it. Let's remind ourselves again why that formula worked. When we plug in a into P3, if we're looking at P3 of a, we're left with just f of a. And the reason for that is that each of these other terms has an x minus a in it, so they're all going to disappear and go to 0 when we plug in a. Let's look then at the derivative. If we look at P3 prime, then the f of a term disappears because it's a constant. We get f prime of a, x minus a goes to 1, plus now we have f double prime of a over 2, times, now when we take the derivative of x minus a squared, we bring down a 2, and we're left with an x minus a. And when we take the derivative of x minus a cubed, we're going to bring down a 3 and be left with an x minus a squared. And now if we were to plug in a, we would keep the f prime of a, and all the other terms would disappear because they have an x minus a in them. Now let's look at the second derivative. The f prime of a disappears. The f double prime of a over 2 times 2 stays, and those 2's are going to cancel. The x minus a, when you take its derivative, it's 1. And let's look carefully at what happens to the f triple prime of a over 3 factorial term. We have the 3 we brought down before, and now we're going to bring down a 2 from taking the derivative of x minus a squared, and we're going to be left with x minus a to the first. Now if we look at p double prime of a, we would be left with just f double prime of a because this last term has an x minus a in it. It goes to 0. So now we'll look at the third derivative, and we'll be left with f triple prime of a over 3 factorial times 3 times 2 times 1. So there's our 3 factorial on top. That will cancel with the 3 factorial on the bottom and give us the f triple prime of a that we want. So what did we want to see out of this? Note that every time we took a derivative, let's look at this cubic term. Every time we took a derivative, we brought down one lower number until eventually we were left with a factorial of the number we started with in the power. And I want to argue that if we were to look at a general x minus a to the n term and take n derivatives, the exact same thing would happen. After the first derivative, we would have n times x minus a to the n minus 1. After the second derivative, we'd have n times n minus 1 times x minus a to the n minus 2. If we were to look at the third derivative, it would be n times n minus 1 times n minus 2 times x minus a to the n minus 3. And if we did this enough times, we would end up with n factorial times x minus a to the 1, and the next derivative would give us just n factorial. And so what does this mean? This means that every one of our terms, x minus a to the n, when we take its derivative enough times to get rid of it, we're going to be left with an n factorial. And so how many times are we going to have to take that derivative? Well, if this was the nth polynomial, and we had a whole bunch of stuff we were adding up here in the front, and then in the end we had this x minus a term, then we would have the first derivative, the second derivative, all the way down to when we take the nth derivative, we're going to be left with just n factorial. Now the question we're trying to ask ourselves is, in our Taylor polynomial, what should the constant be in front of this term? So let's put the constant in here. And we can come down here to the bottom and we can solve for it. Our nth derivative of our p sub n polynomial, our nth order polynomial, is going to be just c times n factorial. All the other terms will have disappeared. And now what's the condition we want it to meet? The condition we want the nth order polynomial approximation to meet is all the conditions of the previous polynomial. So all the terms before will be just like the earlier polynomials. But then we also want the additional condition that p sub n, the nth derivative at a, should equal f the nth derivative at a. So combining these two statements, we get that the nth derivative of f at a should equal c times n factorial, or that the constant in front of the x minus a to the n term ought to be the nth derivative at a divided by n factorial. So what does that tell us? That tells us that for every k starting at 0 and going up to n, our terms of our Taylor polynomial should look like the kth derivative of a over k factorial times x minus a to the k. And that's how we're going to write p sub n of x for all n. Here we have a problem that says find the nth order polynomial approximation if f of x equals natural log of x, and we want this approximation to be centered at x equals 1. We've previously found the third order polynomial approximation of ln of x centered at 1, but now we need to figure out a way to generalize this. So what did we do? When we did the first, second, and third order approximation, and every time we took derivatives and then plugged in 1. And what we really would need to do if we want to find the nth derivative here is we need to find a pattern in these derivatives at 1. So let's start by taking derivatives, and let's see if we can do it without simplifying. So let's write f of x equals natural log of x, then f prime of x equals x to the negative 1, f double prime of x equals negative 1 x to the negative 2, f triple prime of x equals negative 1 times negative 2 times x to the negative 3. The fourth derivative of x equals negative 1 times negative 2 times negative 3 times x to the negative 4. And we can see there's definitely a pattern here, right? And it looks like it should involve a factorial. The fifth derivative is going to be negative 1 times negative 2 times negative 3 times negative 4 times x to the negative 5. And so what is this pattern actually going to be? Well, let's look at the nth derivative. Let's look for a pattern. So every time I take a derivative, I get a new negative sign. So I'm changing signs. I'm alternating. So there's going to be a negative 1. It's either going to be to the n or the n plus 1. So let's look at, here this is the first derivative, the second derivative, the third derivative. All right, so what is the pattern? When n is 1, the derivative is positive. When n is 2, the derivative is negative. 3 is positive, 4 is negative. So we get negative numbers when n is even, so we want this to be to the n plus 1. Now, look at what the terms are going to be in our factorial. When I am looking at the third derivative, when n is 3, I have 1 times 2. When n is 4, I have 1 times 2 times 3. When n is 5, I have 1 times 2 times 3 times 4. So I always have 1 less than whatever n is. So it's going to be n minus 1 factorial. And then it's x to the negative n, because the power of x is always negative whatever number derivative I'm on. So this is a general pattern for the nth derivative of x. And that means then we can find a general pattern for the nth derivative of 1 by just plugging 1 into this. So we get negative 1 to the n plus 1 times n minus 1 factorial times 1 to the negative n, which is just negative 1 to the n plus 1, n minus 1 factorial. And the other thing we want to note is that this pattern does not work when n is 0. So if we wanted to write a general polynomial sub n of x, we would have to put the 0th term here, f of 1, out by itself. So we would have f of 1 plus the sum k goes from, this is the 0th term, so we're going to start at 1, k goes from 1 to n, of, now I found my pattern for my derivative, so it's negative 1 to the k plus 1, k minus 1 factorial, all over, and I know I divide by k factorial, right? Because I should have my derivative divided by k factorial times x minus 1 to the k. And I can simplify this a little bit. I can say p sub n of x is well, f of 1 is natural log of 1. And now I'm doing the sum, k goes from 1 to n, of negative 1 to the k plus 1. And what happens if you have k minus 1 factorial over k factorial? Well, that just gives you 1 over k times x minus 1 to the k. And if we simplify one more time, p sub n of x, natural log of 1 is just 0. So this is just the sum, k goes from 1 to n, of negative 1 to the k plus 1 over k times x minus 1 to the k. So that doesn't look so bad now that we're done. And we can even use that formula now pretty easily. If we wanted to find p sub 4 of x, we would say that that was the sum, k goes from 1 to 4, of negative 1 to the k plus 1 over k, x minus 1 to the k. If we wanted to actually approximate natural log 1.04, we know that that's approximately p sub 4 of 1.04, which would then equal the sum, k goes from 1 to 4, of negative 1 to the k plus 1 over k, 1.04 minus 1 to the k. And of course, we would have to write out all 4 of those terms and calculate out what they were to get our actual approximation. And if we were to do that, we would get p sub 4 of 1.01 is equal to 1.04 minus 1 minus 1/2 times 1.04 minus 1 squared plus 1/3 times 1.04 minus 1 cubed minus, can I squeeze this in here, 1/4 times 1.04 minus 1 to the 4th, which turns out to be 0.04 minus 0.0008 plus 1/3 times 0.00064 minus 1/4 times 0.0000256. And that's going to give us 0.0392206,933 repeating. And we could compare that with the actual calculator value of natural log of 1.04 to see if we're actually anywhere close. And that calculator value is 0.03922207132. So you can see that, we're correct up through the first 1, 2, 3, 4, 5, 6 terms. And after that, we're pretty close, but we're not exactly right. This problem asks us to estimate the error in approximating natural log of 1.04 using a fourth order Taylor polynomial for f of x equals natural log of x centered at x equals 1. So we've just actually found this estimate, right? And we actually even compared with the calculator value and said that for about the first 6 decimal places, it looked like it was correct. But let's use the Taylor's theorem to get a bound on this error and see if it makes sense compared to what we've already found. All right, so according to Taylor's theorem, the remainder of the fourth order term for a value x is equal to the fifth term, essentially. So the fifth derivative of f at a divided by 5 factorial times x minus a to the fifth, with the difference that the fifth derivative is not evaluated at a, it's evaluated at some point c. And what do we know about c? We know that c is between a and x. So maybe we need to go back and look at the derivatives again. So we had f of x equaling natural log of x. F prime of x was x to the negative 1. F double prime of x, negative 1, x to the negative 2. F triple prime of x was negative 1 times negative 2 times x to the negative 3. The fourth derivative at x was negative 1 times negative 2 times negative 3 times x to the negative 4. And the fifth derivative at x, which is the one we need, was negative 1 times negative 2 times negative 3 times negative 4, x to the negative 5. So if we multiply all those together, we get 24 x to the negative 5 is our fifth derivative. So our fifth derivative at some point c is going to be 24c to the negative 5. All right, so putting that in the remainder theorem then, we get that our remainder sub 5, or our remainder sub 4, right? We're looking at the fifth term, but it's actually the remainder for the fourth degree polynomial of x is 24c to the negative fifth over 5 factorial times x minus, our a here is 1, so x minus a to the fifth. And we're looking at our x value being 1.04, so we can plug that in. We're looking actually particularly for r sub 4 of 1.04. That's the point we're trying to estimate, so we're going to get 24c to the negative fifth over 5 factorial times 1.04 minus 1 to the fifth. Now the problem is we don't know what this value c is. So what we want to do is we want to take our fifth derivative at x, which was, remember, 24x to the negative fifth, and we want to find the maximum value on the interval 1.04. And the reason we want to do this is it's going to find our big M, is we want to replace 24c to the negative fifth with its maximum value on the interval. Because we don't know what c is, we can't find an exact value for 24c to the negative fifth. But if we replace it with its maximum value on that interval, we'll get a number that is a pretty good estimate for the remainder. So what can we say about this? Well, we want to find the absolute maximum of a continuous function on a closed interval. So we want to look at its derivative. So the sixth derivative of f of x, which is the derivative of the fifth derivative, is 24 times negative 5 x to the negative sixth. And we can see that that's always negative. So this function is always decreasing. So it doesn't have any critical points in the interval from 1 to 1.04. It does have a critical point. Notice at 0 it would be undefined there, but that's not in our interval. Remember, critical points we're looking for where the derivative is 0 or undefined. So the absolute max must occur on an endpoint. All right, so the endpoints are 1 and 1.04. So the fifth derivative of f at 1 is 24. And the fifth derivative at 1.04 is 24 times 1.04 to the negative fifth. Now, since we're taking a number bigger than 1 and raising it to a negative power, that's going to give us a number less than 1 here. So this one is less than 24. So the maximum value is going to be the 24. So we're going to go back to our remainder, sub 4 of 1.04. And we're going to say that that has to be less than or equal to 24. We're replacing 24c to the negative fifth with 24. That's its maximum value. That's the big M. Over 5 factorial times 1.04 minus 1 to the fifth. And now that's just a number we can calculate. So we get 1/5 times 0.04 to the fifth, which is 0.0000000248. So pretty darn close. All right, let's look at a slightly more complicated problem. This one says, what is the maximum error in approximating e to the x by the fifth order polynomial for values of x in the interval from -2 to 2? So that interval is going to give us a little bit of a problem. The other thing that's going to give us a bit of a problem is we haven't actually found a formula for the fifth polynomial approximation of e to the x. So we need to start with that. And I guess it should say on here where we want to center it at. So let's pretend it said centered at x equals 0. All right. So what do we need to do first? We need to actually find the polynomial. So let's start by looking at derivatives. F of x equals e to the x. F prime of x equals e to the x. Wait, they're all going to be e to the x, right? The fifth derivative is going to be e to the x. Okay, so that makes that pretty simple. That means that when I plug 0 in, I'm going to get e to the 0, which is 1 every time. F prime of 0 is 1. The fifth derivative of 0 is 1. Every derivative at 0 is 1. Well, that means that we can pretty quickly figure out that p sub 5 of x is going to be 1 plus 1 over 1 factorial x minus 0 plus 1 over 2 factorial x minus 0 squared plus 1 over 3 factorial x minus 0 cubed plus 1 over 4 factorial x minus 0 to the 4th plus 1 over 5 factorial x minus 0 to the 5th. And that's just because every one of those derivatives evaluated at 0 gives us 1. So if we want to approximate the remainder, we want to look at the remainder sub 5 of x, and we know that that's going to be the 6th derivative. But remember, now this is at this point c that we don't know what it is. It's just in the interval. Over 6 factorial x to the 6th. A is 0, x minus a is just x. And this is for some c between 0 and x. Alright, so now we want to figure out something about this. Well, we know something about the 6th derivative. We know its formula. So we can say that r sub 5 of x is e to the c over 6 factorial x to the 6th. Alright, but now what? What can we say about e to the c? Well, we want to find the maximum value of e to the c for c in negative 2 to 2. Why do we want c in negative 2 to 2? Well, it's c between 0 and x is between negative 2 and 2. So if we want to consider all the c's between x and 0, for any x between negative 2 and 2, c could get as small as negative 2 or as big as 2. Alright, so what can we say about e on that interval? Well, we want to look at its derivative, see if it has any critical points. So the derivative of the 5th derivative of x equaling e to the x is the 6th derivative of x, which is also e to the x, which does not equal 0 and is not undefined between negative 2 and 2. So no critical points. So we just need to look at the endpoints. We want to look at the 5th derivative at negative 2, which will be e to the negative 2, and the 5th derivative at 2, which will be e squared. And hopefully that's pretty clear that the e squared is the bigger number there. So that's our m, our max value. So we can stick that in. We can say r sub 5 of x is going to be less than or equal to e squared over 6 factorial x to the 6th. But now we still have this x in our equation. So we want to find the maximum value of x to the 6th for x in negative 2 to 2. And since we know that we have an even polynomial x to the 6th, we know that its maximum value is going to occur at one of these endpoints, and it doesn't matter which one you plug in, you're still going to get the same value once you take an even power of it, since this interval goes from negative 2 to 2, negative the same number to that number. But again, you could do the same test that we did before. If you really wanted to, you could take the derivative of x to the 6th, look at the critical points and the endpoints, and determine that the maximum value is going to be 2 to the 6th. So now we can put that in too and say that r sub 5 of x is less than or equal to e squared over 6 factorial times 2 to the 6th. And maybe we don't know what e is. In fact, if we knew what e was, we probably wouldn't be doing this at all. So let's bound one more thing. Let's say that e is less than or equal to 3. In fact, it's strictly less than 3. So let's replace e with 3. R sub 5 of x is now strictly less than 3 squared over 6 factorial times 2 to the 6th. And that number turns out to be 0.8. So our maximum error is less than 0.8. All right, let's try one more example. This one gets even more complicated though. This one says, how many terms of the Taylor polynomial are needed to approximate sine of x with an error of less than 10 to the negative 6th on the interval from negative 1 to 1. So we need to come up with a general idea of the nth polynomial for sine of x. Well, let's start taking derivatives. If f of x is sine of x, then f prime of x is cosine of x, f double prime of x is negative sine of x, f triple prime of x is negative cosine of x, the fourth derivative is sine of x, and we're back where we started, and it just keeps repeating. So if we want to look at the interval from negative 1 to 1, it might make sense to center this at 0, since we know what sine of 0 is and we know what cosine of 0 is. So let's set that into the problem here, centered at 0. So f of 0 is sine of 0, which is 0. F prime of 0 is cosine of 0, which is 1. F double prime of 0 is negative sine of 0, which is 0 again. F triple prime of 0 is negative cosine of 0, which is negative 1. The fourth derivative at 0 is back to sine of 0, which is 0 again. And what you can see what's going to happen here is it's going to go 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1, 0, negative 1. So it's alternating, sort of, but it's skipping every other term. Let's actually write out what p sub n is so that we know what we're plugging into. So this is f of a plus f prime of a over 1 factorial x minus a plus f double prime of a over 2 factorial x minus a squared plus f triple prime of a over 3 factorial x minus a cubed plus dot 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 f the nth derivative at a over n factorial x minus a to the n. All right, so that's the general nth order Taylor polynomial. Now let's look at sine. So we know that f of a, f of 0 would be 0, plus f prime of a is f prime of 0 is 1 over 1 factorial, and x minus a is 0, so that's just going to be x, plus f double prime of a is 0 again, so 0 over 2 factorial, x squared, plus negative 1 now over 3 factorial, x cubed, plus 0 over 4 factorial, x to the 4th, plus 1 over 5 factorial, x to the 5th, plus dot dot dot. The nth derivative at 0 over n factorial x to the n. And we can simplify this a little bit. We can actually see that p sub n of x is going to be x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th plus 1 over 9 factorial x to the 9th plus dot dot dot, wherever we end here, the nth derivative at 0 over n factorial x to the n. So the question is, how many of these terms will we need to approximate the function sine of x with an error of less than 10 to the negative 6th on the interval from negative 1 to 1? So what can we say? We can say r sub n of x is equal to f sub n plus 1 of c over n plus 1 factorial x to the n plus 1. For some c between 0 and x. And we know x is between negative 1 and 1, so we end up with, for c, in the interval from negative 1 to 1. All right, so we want to find the absolute maximum of the n plus 1th derivative. And I guess I should have been saying all along that we actually need the absolute value of the n plus first derivative at c, because we're looking for the error, whether it's too big or too small. We want to reduce that error. So let's look at the absolute value there, since this function actually is sometimes positive and sometimes negative. So what can we say? Well, we know that the nth plus 1th derivative is either going to be sine, cosine, negative sine, or negative cosine. So if we consider the absolute value of sine of x and the absolute value of cosine of x, then we should be good. But notice that the absolute value of sine of x is always less than or equal to 1, and the absolute value of cosine of x is always less than or equal to 1. So we can state that the absolute maximum of the absolute value of the n plus 1st derivative of f with c plugged in there is no more than 1, because it's something that you got out of a sine or a cosine. And that works no matter what your value of c is. All right, so how does that help us? That tells us that our remainder sub n, and let's look at the absolute value of that too, is always less than or equal to 1, replacing that derivative term with a 1, times the absolute value of x to the n plus 1 all over n plus 1 factorial. But we know that x is in the interval from negative 1 to 1. So the maximum value of x to the n plus 1 is also 1. So we can replace that. So we can get r sub n, the in absolute value, is always less than or equal to 1 times 1 over n plus 1 factorial for x in the interval from negative 1 to 1. Now remember, we want the absolute value of the remainder to be less than or equal to 10 to the negative 6th. Actually, I guess we wanted it to be less than 10 to the negative 6th. So let's let 1 over n plus 1 factorial be less than 10 to the negative 6th and figure out what value of n we need for that. Now, we don't really have a great way of solving for n here with the factorial, so we're just going to do this by trial and error. So let's plug in a few numbers. If we try 1 over 9 factorial, that one turns out to be bigger than 10 to the negative 6th. But if we try 1 over 10 factorial, that one actually is less than 10 to the negative 6th. So we're going to let n plus 1 equal 10, which tells us that our n is 9. So we need a 9th order Taylor polynomial to ensure that our error is less than 10 to the negative 6th on the whole interval from negative 1 to 1. And what would that Taylor polynomial look like? Well, we already figured this out. This would be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial.